Hi everyone. Today we will see multithreaded sorting versus sequential sorting. We will understand why we need multithreaded sorting and why we can't keep on using sequential sorting and different aspects of this particular project. As we can see, firstly we will understand the introduction to sequential sorting using merge sort. Then we will understand history and some background on it. We will see sorting using merge sort and how it is performed. Then we'll see parallel processing and hardware. We will see problems of single processor sorting. After that, we will see parallel sorting using merge sort. We will see results of experiments that we do. We will understand some advantages and some disadvantages. We will see some conclusions that can happen, and then we can basically things that we can conclude, and then we can see some references. So let's go and understand all this. So as I was saying, an example of sequential sort is basically selection sort. As we can see, in selection sort, the time complexity for sorting a particular array of unsorted elements is big of n squared, whereas the sorting complexity, time complexity of merge sort is big of n log n. This is because merge sort runs on a divide and conquer algorithm and basically divides the input array in multiple different operations and then performs them sequentially to come to an output which gives us a much faster output to an unsorted array. And this is why it is better than selection sort, and that is why it is one of the best sorting algorithms in sequential sort. It is also used at an industry level and is used also in timsort, which is actually a sorting algorithm in Python. Let's go ahead. Now let's understand some history and background of merge sort. Merge sort is a divide and conquer algorithm that was invented by John von Neumann in 1945. He was a brilliant scientist at the time. He invented this algorithm basically because at the time in the United States, different people were voting and their votes had to be sorted, their vote cards had to be sorted, and that kind of sorting took a lot of operations. And he basically developed this particular sorting algorithm so that this particular sorting task of different voting cards could be performed faster and more conveniently. A detailed description and analysis of bottom-up merge sort appeared in a report by Goldstein and von Neumann as early as 1948, when he first actually wrote a report on it with Goldstein. Apart from that, Donald Knuth, in his Art of Computer Programming book in volume 3, Sorting and Searching, attributes the sequential merge sort to John von Neumann. He says that this person is a total genius, and him coming with this particular algorithm was not something that he came up out something out of thin air, but rather he devised how he will make it. He personally worked really hard and then came up with this algorithm, and he is looked up by the mathematical polymath community ever since then. Now let's understand what he basically made, and we will understand sorting using merge sort. So in merge sort, you have an input array which has unsorted elements. Now this can be also voter cards or anything else which needs to be sorted. But there should be some distinction, and of course you will code the operations which will be performed for sorting. Coming down, this particular array is broken down into smaller parts. As you can see, it's nearly halved over here, and then it gets halved further and further till each element is a standalone element, as you can see over here. After this point, each element will interact with one another and sort themselves into making a length of 2, as you can see over here. And now this keeps on going on till bigger, as you can see, a bigger sorted different arrays which are basically running on divide and conquer and basically getting divided first and then merged together by the merge operation, are basically getting merged. So it first gets divided and now it starts getting merged and gets sorted, as you can see over here. And then going forward, it gets sorted into bigger arrays over here till finally the main sorted array is given out as output, as you can see over here. This is how merge sort runs. So understanding that it runs on basically a divide and conquer approach is what we have to understand first is how it is working, in fact, and this is how it works. Now let's understand something about parallel processing and hardware. And this is because this is why we are actually doing this. This is why we are at the point that we need to use all the parallel hardware that we have for sorting. Parallel processing on multiple processing units as an idea dates back to the 1950s, with its subsequent development till date. So since the 1950s, we see that parallel processing on multiple processing units have been devised, and it was first devised by two people working at IBM, who later started developing such systems at IBM within a matter of 2 years at a global level. And that is why today we have multi-core, multi-processor logical unit processing systems with multiple worker nodes and everything. Going forward, we understand that parallel processing gave programmers a capability to use multiple processors and divide the workload among these processors. So what it basically means that we take multiple processors and then we divide our workload over these multiple processors, which are basically our worker nodes. So if this is the system and these are the databases and some operations are coming in, then whatever operation comes in gets divided among these processors. The work gets divided among these processors. It breaks down. So each processor does only a certain number of operations to its bottleneck, and it doesn't has to go ahead of its bottleneck and make queues, which would lead to wait times and subsequently lead to issues of delay. Going ahead, we see that merge sort by its design is a divide and conquer algorithm, as we understand merge sort. So merge sort, being a divide and conquer algorithm, should use multiprocessing and multiple threads to run to give higher speeds for bigger sorting operations, which was quite easily logical, and that is why researchers developed its parallel implementation to further use it to its full potential as a sorting algorithm. And this is basically discussed in this presentation going forward. So going ahead from this point, so problems of single processor sequential sorting. As you can see, as sequential sort runs on a single process, it is slow as it does not use the capability of modern hardware and is slower than parallel implementation of the same algorithm. Because in modern hardware, we have multiple core units and multiple CPU units, multiple logical processors, and they can all run their operations parallelly rather than running them sequentially. And so we can have much more higher speed of work. It is just like if two people are doing the same task rather than just one person, the division of their workload would save us time, and this division goes on with a higher number of working nodes are on one operation, which can, if that operation can be divided, then that same amount of time can be saved. Merge sort by design divides its tasks and merges them subsequently. Therefore, running these tasks sequentially takes way more time than in parallel. And therefore, merge sort, when run in parallel over multiple processors, in fact, gives us very high speed, which we will understand going forward. Now we go to the core of the matter where we will spend most of our time. Parallel sorting using merge sort. The parallel implementation of merge sort uses a binary tree of processes to sort and merge the input shuffled array of elements. What does this mean? This means that, for example, as we can see, a sequence of numbers, an array or sequence of numbers comes in and we have to sort the sequence of numbers. So how will we do this? We can use a tree structure because, as you can see, merge sort by its design looks like a tree with nodes, wherein there are the tree nodes and edges, which basically are merge operations, which are merging data together and sorting them in nodes. That is why binary tree is a good implementation for parallel merge sort, and that is why we have used that. The future on the figure on the right shows a binary tree that has to sort for integers. The tree consists of several processes that are simply its nodes and 8 communication channels that are its edges. So as we can see, there are 4 integers in this particular figure, which have to be sorted. The nodes in this particular these nodes are basically processes which are in the binary tree. So these are processes which are running. There are 8 communication channels, as we can see, and these are the edges. These 8 communication channels are basically connection between these processes, which basically send a message from this to this process. It can be a single integer, it can be an array of integers, and that is how a binary search tree basically a binary, sorry, not a search tree, but a binary tree implementation is basically being used. Initially, a tree is created in a recursive manner, that it is initially made in a recursive manner. As trees have to be created, they are basically created recursively. So mainly the environment activates the root, which then activates the 2 children, which in turn activates their own children, and so on until the leaves have been activated. All processes in the tree now run in parallel. So basically we see that when an initialization occurs of this binary tree, it is recursive in nature. That each process over here is basically getting activated as a child process, and they basically merge together to give the final output, and they are all parallel processes which are running together and syncing together. So this is what parallel sorting using merge sort is, and this is how it's implemented, and that is how it is done. So we see when the children are all single elements, they merge one by one with the other and for a length of 2 values in an array, and subsequently merge forward for the final sorted list as depicted. So 1 and 1 getting sorted together, these 2 processes merge into a single process with a single array, and then we get a final output array, and that's how merge is subsequently moved forward. And this is how parallel sorting using merge sort works. Now let's go ahead. Results of our experiments. Now this is what we found, and this is what we understand of it till date. So I ran multiple experiments running parallel and sequential merge sort, and I basically wrote some code for parallel merge sort versus some sequential merge sort. I ran iterations of it, and then I collected those values and I graphed them for you to understand what exactly is happening over here. So as we can see, the collected values on those iterations for parallel merge sort were these, for regular merge sort were these, and size of unsorted array was this, as we can see over here. So when to understand this in more detail, we see that initially parallel merge sort takes way more time than sequential merge sort, as you can see, and let's see why that is happening. What can be understood from the graph on the right is that initially a smaller length of unsorted arrays, sequential merge arrays sent in input, sequential merge sort performed much better on it as it did not have to manage multiple threads over multiple processors. So clearly, as you can see, sequential sort got a smaller size of unsorted array, and same was given to parallel merge sort, and sequential sort didn't have to run multiple calculations or basically multiple operations to run those parallel threads together and merging them together, but it ran everything sequentially, and that is why it was faster. That is an example that, for example, I'm doing a work that has to be done by one person, that like pick up a glass. Now that's a fast operation. Now if multiple people are asked to pick up that same glass, it would take way more time for everybody to do that than a single person to do that. And this is somewhat like that only. In this particular case, the sorting operation is so small that when you run it on multiple processes, it takes way more time because those processes themselves take time to get started, initiated, to do their work, and then to end. And that is why we can see that it takes way more time initially by parallel merge sort in comparison to regular sequential merge sort. But as soon as the array size increases, parallel merge sort started taking way less time, and it kept its output speed quite consistent as it could use the true power of multiple cores and provide high speed performance of sorting. As we now understand that we can use the power of multiple cores and multiple logical units together, so we can actually use all these things together, and then we can give a particular output for whatever we are doing. So as you can see, as the array size increases, its time actually started decreasing in comparison to merge sort, whose time started increasing because it was way better for these increasing sizes of unsorted arrays, because it was using multiple cores to process this data, so it was taking way less time than the regular merge sort, and it kept that quite consistent throughout, even with such high values. That is, and these, by the way, are unsorted array size in millions. Okay, so as you can see, it's going in millions. So when you're going so high, even at those level, parallel merge sort just completely won from regular merge sort because it was using the power of modern systems using multiple cores. And that is why, as you can see, the tree structure that we saw in the previous slide was so important, as it shows us that multiple processes running together actually need multiple cores, actually need those logical cores. It explains why these processes are running in parallel rather than in a sequential manner. It was developed recursively, it got initiated recursively, and it then gave it output using the power of so many processing cores. And this is how we basically understand that all these processes that are running together are that much very fast, because they are using the power of multiple core and processes versus a single processor that would actually die running so many of operations on itself. Now let's go ahead and see some other stuff. So now, what are the advantages and disadvantages at a peak? The advantages of sequential versus parallel sorting for merge sort, at least, is that for sequential, it's faster for smaller sorting processes, that it does not have to merge parallel running operations, and handle multiple processor inputs output operations. Therefore, as it is not handling so much of overhead of multiple threads running around, it does not have to care about running all the operations and syncing them together later on, and that is why it is faster. Now, for parallel faster, it's faster for larger sorting process with millions of values to be sorted, but it is slower for sequential, and therefore you have to see what kind of data set you're using it on and not to use it just anywhere just because you have an option to do so. Now, going forward, sequential uses less hardware and allowed other processes to get CPU as well. So when you're running multiple processes and they're not all about sorting, sequential sorting would be a much better option for you because it gives other processes a chance to use the CPU as well, and it does not totally utilize your resources to do one operation. So it is very good for a distributed system where multiple operations are being run. But if it's being run on a single system, which actually denies a little bit of what a distributed system is, but even if it's running on a single system and multiple processors have to be run on multiple CPUs, then sorting is not the only thing has to be done, and sequential sort is very good for that. Coming to parallel, we see that uses proper capability of available resources and does not waste time and resources. So if sorting is that much important and you want to get the output before you run any other process, then parallel sorting is the winner, clear-cut winner over here, because it uses all the CPUs and every particular resource it can get in those logical CPUs to give you an output as fast as possible. It does not waste time and it uses all your resources that you provided. It makes a lot of threads, it does a lot of operations, but it gets the work done in very fast, and we'll see how fast it really is. But before that, let's see the last point on sequential over here, that it is easy to implement and it uses many is used in many industry solutions. Sequential sorting, as it is easier to implement because you don't have to work again with so many operations. You don't have to, the programmer doesn't have to care about so many operations, doesn't have to code everything up so delicately. It doesn't have to code tree structures which are recursively running in parallel, but he has to only run the basic merge sort algorithm, and he can actually give a proper output on that rather than, wasting his time on something which he doesn't need to do. This is also being used in the industry, in many industry solutions, because it is fast. Most of the data which has to be sorted is not so big in size, and it gets the job done at the end of the day. Let's go, and it is also used in TimSort in Python as I understand it. Now let's understand parallel. Used for nearly big of n time complexity of sorting on big of log n number of processors. So as we can see, as we are using multiple processor, it gives big of n time complexity of sorting that is very, very fast for a sorting operation, wherein there are big of log n number of operations. This particular thing is quite remarkable in our industry, as we have understood that even the fastest sequential algorithms have given us only n log n time complexity of sorting, wherein the same implementation of those algorithms in parallel bring us down to big of n. This shows that we have a lot of potential in the parallel processing industry, and why using multiple CPU cores has become utmost important in the industry today. Now, as a conclusion, we see that as understood in previous slide, parallel merge sort is perfect for very large sorting operation. It gives us big offense sorting time complexity, which is very fast for this type of problem. Sequential algorithms are good for small data sets, but not large data sets. Parallel processing is the future and will the usage of multiple core processors will only increase towards the future. It basically means that we will be using multiple cores in way more in the future than we are using them currently, and we will be using them in a very efficient way to get the job done as fast as possible, as these technologies are the future, multiple cores of the future. Some references over here are again by Nuts, The Art of Computer Programming. This is a very good reference, I would say, and I suggest everyone to give it a read if they can. And of course, The Analysis of Parallel Merge Sort by Mr. P. Bridge Henson. And this is actually what actually talks about parallel merge sort, and I do give you a suggestion to read this if you do have the time. I would like to thank you all for giving me your time today, and I hope you learned something from this presentation. I look forward to giving such more educational content to you going ahead. Thank you for giving me your time today. Have a nice day.